Chance, we covered in the last class the functional language features, iterators, and closures. That was the one that we certainly had some difficulty with. And then we also covered the IO project, building a command line program. So that was our first work through of processing arguments and using standard in and all the other kind of stuff. If we have any questions on that, I'll answer them. If not, we're going to kick it off today with cargo and crates.io. Okay? So far we've used cargo quite a bit. We've become pretty good friends with cargo. Today we're going to be talking about a couple of more things with cargo, more advanced functionality. Cargo gives us the ability to do a lot of things with conditional code. It gives us the ability to do quite a bit of things too with regard to development builds and release builds. These things are called profiles. And we get to see about some of those things we can do and how we can customize it and how it works. Let's kick it off with profiles. It's pretty simple. There is a profile for a development build and a profile for a release build. And you can specify different things in cargo to customize those two different compilation pieces, right? For a long time, I want to say a release profile did not have, it had your symbols in it, your debug symbols in it. So even though it was a release profile, you could still debug it. I believe recently they have removed that. So it's now stripped out. That is not mentioned in the book, but I guess someone could validate that by a quick Google search. But I believe that's now the case. In the book, they're using optimization levels, opt level, as an example of an optimization that they have here. They're effectively saying when we're developing things for the development profile or compiling things for the development profile, we do not want optimizations. And when we have it for the release profile, we want the most optimizations, which Rust calls 3. If you ever use the real compiler directly, like GCC or Clang or something like that, they usually have either an itemized list of optimizations, in which case there's thousands of them, or multiple different levels, more than 3. But Rust kind of makes this slightly simpler. This is effectively your interface into that compiler chain, and you have 0 through 3 are your options here. Now, I don't know anyone who's ever used optimization level 2 or 1. Generally speaking, you want all of the optimizations or none of the optimizations. But you know, here's where you can set that kind of stuff up. And there's a lot of different things people will optimize in development builds and in production builds. You know, I've seen. What's up?
For example, if you're building for, if you're targeting WebAssembly, you want to optimize for files.
Yes, frequently. Yeah.
Which is
yeah.
Very different.
There's a whole thing for building WebAssembly stuff too. It's called it's not clap. It's another one of those like clever things though. Let's see here. It's called the Rust Cross Compiler framework, I think. I believe this is still what they end up using for WebAssembly, and it is. Yeah. Well, now maybe it's not even required. This doesn't look like it's using it anymore. It's been a while since I compiled things for WebAssembly or for cross-compiled it. But there used to be something else that had like a really gimmicky name, and I forget the name of it. Dun, 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 dun. Anyway, we can play with that later. They've apparently changed some things on it. So let's go ahead and hit on this. When we have this crate, one of the things that we can do with it is because we have unified how we develop code and deploy it locally, it is the same way that crates.io accepts that code. It has all of the same components into it. So in some languages, you can develop your code and deploy your code in a different fashion than the online repositories will accept, right? And this means that making your code acceptable to an online repository requires a lot of work. I'll give you a case in point. cPanel is Perl. Perl uses an online repository called cpan, and yet cPanel is not ready to ship cPanel code to cpan. And the reason is our code looks totally different. We're an enterprise, right? So in Rust, even code written by enterprises and by businesses, it's effectively ready. If you jumped into it and you typed in cargo publish, and they didn't set the private flag in their cargo toml to stop people from doing this, you could mistakenly publish the entire code base. It'd be that simple. It's already ready to push it up. That is really nice. It's really always that simple because we start off with it. That's one of the reasons why, if anyone was here for class 1, where we went through and we started using Rust C, and I said no one actually writes code like this, I mean it. When we start off code, we start off with cargo, and cargo, even the demo project, could be named properly and pushed up to crates.io. It will take it, right? So they're effectively telling you here how a sample piece of code works. So they're showing you again what 3 slashes mean. Does anyone remember? We already went through this.
Online publication, or where it makes like the whole web page thing?
The 3 slashes mean it's a code comment, right? It's a code comment. So we're commenting on the thing below it, right? And that comment it has a target, so it can be used in generating documentation. Whereas if it was, I should actually rephrase that. This is a doc comment and not a code comment. If it was a code comment, it would be for your internal use only. A doc comment is used for the purpose of generating documentation. That's what I mean. It just so happens to be that using 2 slashes means it's a code comment, but if you use a special 3rd slash, even though it's still not processed, it says this comment is special. We're commenting on the thing below us. So you can do that on all your functions, and then that comment will go up to cargo, crates.io, and it'll use it to generate cargo docs, right? Now, you can also run cargo doc in your code and get your web page and have online browsable documentation. So that's awesome. Here's an example of that. We've already done that in class. We did cargo doc in class and we covered that. There's also this other thing we can do with the exclamation point. This is a doc comment, but rather than saying this thing is documenting the thing below it, right? The / exclamation point says this line is documenting the thing that it's contained in. So in this case, we're documenting the crate, the entire thing, right? Or the file. We're not documenting the function or the struct or the enum, right? So this is saying we're documenting that which contains us. It's essentially pointing to the container rather than the thing you're on top of. Exporting an API. Okay, this is tricky, and there really is no right way to do this. So there's a lot of different ideas about exporting in Rust. Some people like to export everything flat. Some people don't. The standard library is an example of a case where everything is not exported flat. So if you wanted to use something in IO, you do use stdio : read from file or whatever, right? But when you oftentimes you make your code, you don't want people to know the thing you're exporting is in IO, right? You just want them to know that they need the function read from file. So you can do these things called pub export, and you can effectively say, this thing that I have access to, I want to export it as if it was declared here, right? So you do pub use, and you say read from file, and now it's going to pull in that piece of code wherever it's at in your project and re-export it. So pub whatever is a good method of making something public. Pub use is a good method of re-exporting something. So you'll see that here we say like use art, kinds, primary color. This is, some people don't like this. It's a style thing. If you like it, fine. You don't have to ever re-export things. If you don't like it and you believe it adds value to your project to hide the structure of your project, you can do pub use, and it just makes it effectively available for other people without having to know the structure inside and where everything is defined. You know, I don't know. I don't really fall on either side of these hard. You know, some people fall on one side. They're like, everything must be exported as if it was a flat file. That to me seems a little silly. And then the other opinion too, that you should never use it. You should expose all of your structure for your module. Also sounds a little bit silly. So I'm like split on this one, you know. But there's definitely people that are on one side or the other. Crates.io is very easy to set up. This is becoming a way that we do a lot of things now with code. You will set up an account and log into an account, and then you'll generally write your token into a file in your home directory, right? Examples of services that do this. If you use GitHub, it has a utility called GH. You'll log into GitHub with GH, and then it'll give you a token. You put that token in your home directory. It's part of your development stuff. Cargo does the same thing. Log in, you get a token. You can put it in your public directory. There's also Cargo login. I think it gives you the ability to run that and do it interactively. You can paste your API key when prompted. There you go. So you log into Cargo online. You get an API key. You type in Cargo login, and you paste that token that you got there. And then it will create the file for you in your home directory with your token. Adding metadata to your file. There is a ton of metadata a cargo.toml file can have, right? Depending on the importance of your project, I suggest filling it all out. It'll have things in there like repository, homepage, contact email, other authors, all that kind of stuff. Give the shout outs where due. You can put in there descriptions. I think they even have like tags. They have a ton of stuff. Definitely read the manual page on a cargo.toml file. Here it is, the manifest format. These are all the things that it supports, you know. Auto bins, auto examples, auto tests, resolver, version, authors, you know, just read these things and have an idea of what they are and what they do. Features is certainly really useful. If your program has optional features, you can declare them as such, and then when people want to install your program, they'll say cargo add and then your library's name, -- features, and the features you want. And that is used everywhere in Rust, right? One of the reasons why that's used everywhere in Rust is because in Rust, thankfully, it is starting to solidify behind different elements of the ecosystem, right? There's less competition than there were in the earlier days, and then that you see in other languages. And because of this, people will implement gigantic features based on that, which you may not want. A great example is a library called Serde. Has anyone here heard of Serde or used it? Okay, this is I'm not sure I'm saying it right either. This is an extremely powerful method of serializing and deserializing data in Rust. So you can take any piece of Rust data, a struct and enum, and you can say, I want to write a Serde exporter for that. You write the Serde exporter, and now Serde knows how to get that data to JSON or XML or whatever else. It has the exporters built into it. So you can take a struct in Rust and transparently make that a JSON message. That's super nice. Let's say you want to model your response for your API. How do you model that response? Write a struct. Put in whatever you want in it. It can even contain another struct. And then you simply say derive Serde. And it will take that whole struct and give you a method to get it to JSON. And we can see that if we want to play with it later. But this type of functionality, Serde, is a very big library. And I would say it has a tremendous amount of penetration in Rust. It's very popular. It is not the fastest way to do things, and some people don't like it, you know? So some feature that adds the ability to export and import from JSON may say this is an optional feature. And when they say it's an optional feature, you now have to request it explicitly. And that is everywhere in Rust. So when you add a package in Rust, it'll tell you what the optional features are, and you can add them in the command line just by saying -- feature. So yeah, we can play around with that too, and I can show you what that looks like. What's up?
How would you serialize enums and pass it over the web to another client that doesn't know the original enums?
You wouldn't. You have to have a deserializer at that point. So if you have the same client built in Rust, Serde will provide the deserializer for you. If you don't have the web client built in Rust with the Serde deserializer, you will have to provide that to your implementer to implement. You know? Make sense?
Yeah.
So when you take in data, it's a text stream, and you say, I want to deserialize that, Serde will say, deserialize it into what? You have to give it a type. You say, the type here is the JSON message. I already declared it in the library. Now Serde knows the type that it needs to deserialize into. It's very easy for it to do it at that point. The question of, well, what happens if you send it to someone who's not using Rust? The answer is, logically, you need to tell them what you can provide in a JSON message, right? So they can take that message and make it make sense in their framework. And that's just part of the communication. When you provide JSON to someone, they would be right to ask you, what are the potential values and the potential schema that you'll be sending over? You know, do you have optional fields in it? That kind of thing. Okay. And just so you know, when you are reading about what other people will provide to you in JSON, there are well-established industry standards that document that. One of them that's very popular is called OpenAPI. So they will write about their API endpoints in OpenAPI, and that will tell you as an integrator what to expect. So one example, this is something that cPanel does right. cPanel has an OpenAPI endpoint. We can go here, docs cPanel API. So we get the actual development documentation. And you come right over here, and here's our development documentation, if I'm smart enough to use it. We'll pretend like this confusion never happened. Get started with WHM, here we go. There we go. This whole thing that we have here, this is all developed with OpenAPI internally. So OpenAPI is a series of like YAML documents you create where you're describing the interface that you expect in a request and that you provide in a response. And then all of this beautiful documentation is generated for you automatically. So there's a tool out there called Redocly, and you can use OpenAPI to generate like a sample document, like a sample. You can use OpenAPI to generate an open source generated documentation like this. Then there's like a Redocly paid service, and what we do is we just take our documentation and we provide it to these guys, and everyone does this. You see like GitHub, Adobe, TripAdvisor, T-Mobile. These are the big players in this industry. And you know, for $300 a month, they will generate and host all your documentation. And all you do is you provide them that YAML file for it. The point that I'm trying to make here is that telling people what you expect in your REST API and what you will provide is very common for most applications. The industry standard way of doing that is OpenAPI, or there's another one called GraphML, which is what Facebook uses. And these two guys that you use to communicate that have the ability to tie into documentation and everything else. So your answer is more promptly, more aptly, you would expect whatever I would document that I'll produce. That's like any language. Rust doesn't solve the problem when I'm communicating with someone that's not Rust. Okay. I sort of disappeared. All right. So now it comes down to publishing the crate. We've already logged in. How do we publish the crate? Cargo publish, that's it, and it goes up. That is a very easy command to mistakenly type. I will tell you that as someone who's done it before. And on multiple networks, I've made that mistake. I love doing Control-R, and it just so happens to be that pub is very common, and I don't know why, but you'll always get it when you least expect it. One of the things I suggest to do is mark your TOML file as private equals true, and then that way it actually won't push up. That's how you do it. So you have like this TOML format, and I think there's, publish equals false, right? You say publish equals false, and then it'll stop you from ever fat fingering that and sending it to cargo, because then it gets listed right away. There's also this feature, cargo yank. This gives you the ability to pull back a version. If you've placed one on cargo and you don't want it there, you fat fingered it, you can actually withdraw it. I would suggest to withdraw packages that you mistakenly publish, like that. Here's the other thing I would suggest. If your package presents a danger to someone else, yank it. If you are literally compromised in your CI pipeline and you have a backdoor in your project or something like that, yank it. Because then you're talking about there's nothing that can be more damaged than giving someone else root access to someone else's machine, right? That's a very high bar. I would say almost anything lower than that, don't yank. Even for security related stuff. Don't yank. Just put out a new version, Because if someone has a cargo lock file and they're looking at your locked version, you'll break all of their stuff. So there's a high risk of damage there, you know? So generally speaking, I've never yanked a package I've never yanked a package that someone else was using. I'll put it to you like that. Never, not once. And my bar for doing that would be very high, intentionally. Cargo workspaces. I feel like that's the, you know, did the officer shoot someone question, you know? Anyway, cargo workspaces. So cargo has this concept of creating library and binary applications, and we use the same format for both of those things. A workspace gives us the ability to put them both together. It is like a super package, right? And the workspace gives us the ability to say inside of it, what are the members? And here's how we do it. We have the members there. And after we have the members, we can just add them. So we add the member right here, declare it as a workspace, and then we can go cargo new adder. And we're now creating a member inside of that workspace. This is an application. Why is this necessary? It's actually not necessary, and I don't tend to do this often. I may do it in the future, but as a creature of habit, I have never found the upside to workspaces, and it is a newer thing. And I think that when I was doing it, they were looked down upon. Frequently, that's the case. The problem is legit, though. So you have a program, and it's using a library. And the question is, how do people want to keep that together? Some people don't like having a repository for a binary application in a library, especially when every update of one means the update of the other. If that is what you're doing, every update of one means the update of the other, the workspace is probably actually what you want, right? This has never been something I actually cared about, to be honest with you. I don't mind having a binary application that uses a library and then having the library slightly newer than the binary application. Generally, it doesn't bother me. When you want that functionality, I push out a new copy of the binary application. I don't necessarily even have to keep their numbers in sync. It doesn't bother me. If that bothers you, here's their solution. I'm happy to go through any of this if anyone cares. I just don't want to get lost in these weeds, you know. This is effectively tooling, and it's kind of boring. How many people here have heard of ripgrep? Good. I like seeing that number go up every time we do this class. Ripgrep is the coolest development tool, bar none. It is the most essential development tool, in my opinion, no matter what language you're using. grep was a very useful development tool, and ripgrep is in every way better. So, and there's no disagreement about that. Everyone likes ripgrep more. It's 1,000,000 times faster. If you don't use it, check it out. It allows you to search through thousands of files instantaneously, faster than any other optimization on Git, on grep, even optimizations with Git. Like, this was a problem when you have lots of files. The question is, how do you search through them all more effectively? One of the solutions for that was called git grep, and it will only search through the files that are checked into the repository. Slightly better, but not all that much. Ripgrep is so fast it can search through all of the files regardless of whether or not they're in a repository quicker. You know, it's just an insane speed improvement. Extending cargo with custom commands. You can do this. You can extend it with custom commands. This is never something I've had to do, right? What it's saying here is that cargo and Git both have the same convention. If you say git foo, it will look for a utility called git-foo, and it'll look for that in the directory that Git is in. So the same thing is true of cargo. Cargo gets installed to, I think it's your home directory, bin, or rather, yeah. Here's where all your cargo binaries are. So you can see here there are some extensions to cargo that I have acquired, like lfix, Miri, cargo RM, all of these types of things. And these extensions are easy for you to implement if you ever want to. By the way, exa is a replacement for ls. And then there's another one in here called lsd. And lsd is amazing, right? lsd is, I think it's even newer than exa, but it gives you the ability to do icons, which is really cool. So if I do lsd, you see icons right here. This is showing these are all runnable programs. And here's one that I think is even cooler than this, though. If I do hyperlink, Now I have clickable links to these things. Actually, yeah, see how it's looking like like I can click it? You see my cursor? Oop, let's do it again. Right there. See how my cursor goes to the finger? I can click these and make it work. It actually generates links for your terminal. Your terminal has special opcodes for linking, and then it'll make it work. It's kind of cool when you have like directories. You can go up a directory or down a directory or whatever by doing this. Like here, let's go back here. Now I see the bin directory. If I want to go into it, I just click it. Well, it's going to launch it in another window, I bet, or something horrible. I'm not sure that this is a good demo. What's up? Well, that's going to show you everything in my home directory. I don't want that. I have work stuff in there. Let's try this here. mkdir tester for I in 1.100 do echo I. That's not useful. And I still fucked that up. There we go. Up, and it's trying to open it up here. So there you go. Let's do here, clear. Now I see a bunch of different files, and if I click on one of them, it'll open it up over here. Let's close these out. I don't actually have an editor that's not made for the terminal. So it tries to open up one in the terminal, and it just guesses the wrong terminal. You know, so now it's got 52 and whatever. Come over here and I click on this one, I get this. Here's a better demo though. If I was to take this and go, let's try this one. Oh. Let's see if it can figure this out. Now I have HTML files. Oh, it didn't open them up in the right browser. All right, we'll play with that later. Sharing code with Cargo and crates.io is part of what makes the Rust ecosystem useful. We already did that. Okay, so anything you want to share, you can share. Smart pointers, all right. So far we've covered references, right? References are, they're considered not smart because they have nothing but a location to data. We've also covered fat pointers, which are still not smart because they only carry with them more information, but not about them. Now we're talking about smart pointers. And smart pointers are pointers that can do things that are clever. So far we've only seen in Rust examples of lifetimes, right? And lifetimes are a method of checking whether or not a pointer is valid at compile time. That's the whole dance, right? The whole dance is this is more difficult for you to write as a programmer, but now the Rust compiler can check to make sure what you expected to happen is actually going to happen, right? And that it's sound, both of those things, right? With a smart pointer, you can do things like create referential data structures, things that point to themselves. You can do things like Perl does, where you have reference counting. Does anyone here know what reference counting is? Reference counting is the act of saying this pointer is used by 5 different places, and when it is used by no places, then you can free up what it's pointing to. So rather than you telling it compile time, this thing is being referenced in your code, and it needs to be alive at this length of time, you can say in runtime, this thing is still being referenced, and you have a counter on it, and as long as that counter isn't 0, you need to keep the data around. And you may ask, well, why do you need that? Well, there's a couple of different reasons why you may need that, but one of them is when things point to themselves, when you create loops. You know, when you create loops, Rust can't test it and say, this needs to live this long, because now, as long as they're making a loop, everything is living that long. So how do you handle that? And you get into the world of smart pointers. Now, of the smart pointers, all of these things have a lot of voodoo. So we have to run through it. Box is a smart pointer that says, this thing I'm allocating, I want you to move it to the heap and return back a reference to it. So box explicitly tells Rust, put this thing on the heap. Do not put it on the stack, right? RCT is a reference counting type. That's the one we just talked about, where we effectively start off with 1 when you have a copy of a pointer, and you start to increment that every time you need a new copy. And now you can have as many copies as you want, and Rust keeps an actual real count of that in runtime. The downside of this is every time you pull out a new pointer, you have to increment something. There's a runtime cost associated with it. The upside of that is now you can do more things with it. You don't have to know what your structure looks like in compile time. Then there's also reft and ref-ut, and well, these are accessed through refcell. And refcell is a type that enforces the borrowing rules at runtime instead of compile time. So you have 2 different things here. We have RC, which is the reference counting, and then we have refcell, and refcell effectively says you can have interior mutability, right? We'll go into some of that very soon. Using box T to point to stuff at the heap, I will say this, box T is one of the few things in Rust that's not actually implemented in the standard library. So to understand what box is actually doing under the hood, you have to know C. There is no code for Rust that does this. So box T looks like this. We can say let B equals box : new 5. And now rather than having 5 on the stack, it is now on the heap, right? And then we have the method there of printing it out. Now, what's up?
Can the smart pointer not outlive the scope, right?
The smart pointer owns the data that it's pointing to with box, right? So you can leak things explicitly and outlive the scope. But by default, when something goes out of scope with box, it will be destroyed. So the smart pointer has the method to destroy the thing it's pointing to. Enabling recursive types with boxes. Let's go in there and look at this. This is called the cons list. This is a definition of a list. So this is interesting if you've never seen it before. If you have seen it before, it's a walk in the park. A list is defined, right, as a list and nil, right? So it's got a self-referential definition. And here's what you see with this. When we have this 3 nil, this is a list, right? And then we have 2 nil, and this is effectively another list. And then we have 1, and then this other list, which is 2, and then this other list, which is 3. We essentially have 3 different lists, more or less nested in each other. This is creating effectively this is creating a list of lists, right? That's what the job of cons is. So a list is defined as cons or nil. Cons takes one element and combines it with a list. That's what the referential definition of a list is. So think about this for a second. It's always weird the first time you've seen it, right? Let's go through this. A list can just be nil. That's totally fine, right? Or it can be constructed with cons. And what does that mean? If you want to construct, remember an enum, we would say it has, the enum type list has 2 constructors, cons and nil, right? To construct a list with nil, it's very simple, just nil. To construct a list with cons, what does it look like? You give it one I32, and then you give it another list. What is the other list you must give it? Well, we've already defined list. It's either nil or cons. So you get this recursive definition.
This is what linked list, right?
Yes. Yeah. Yeah. It's a linked list of an unknown size. You can have as many elements in this list as you want. And it's always defined by one element and a list. Now, if you were writing it in C, the thing that would make it a linked list is the list there in cons would be a reference to a list. In this case, it's not really technically a linked list. Why? Because we're not defining it as a reference to a list. We're defining it as a list. I want you to understand the differences to this, because when you understand the differences to this, you know why it won't work in Rust. Right? This won't work in Rust because cons effectively has to own the list. Right? And for it to own the list, it has to know how big it is that it's owning. Rust doesn't allow you to compile one type of an unknown size. Type must have a known size. Right? So what you're seeing down here is it failing. This is what it would look like if you did it. Right? And when you try to compile it, let's look at that first, and let's understand why it looks like this. Right? List cons1 with another list. It's an I32 with another list. What is the other list? It's cons, and how are we constructing it? With 2 and another list. How are we constructing the other list? Cons is the constructor. We're giving it 3 and nil. Now we know the 3 and the nil is going to make a list. That one always makes sense for people. But notice how cons and the 2 is adding one more element to that. And then cons and the 1 is adding one more yet another element to that. It's effectively, cons is prepending on the list it's given, the element it's given. Right? Cons is constructing that list, right? It's a list constructor. This is all, if you've ever seen a language called Lisp, this is how Lisp works, right? You can do this kind of stuff in Lisp, and it looks just like that. So here's an example of what doesn't work here. It's recursive without indirection. That's its way of saying that. And this is the problem. The problem is you said this is like a linked list, and I said, kind of, right? The reason why it's not exactly like a linked list is a linked list doesn't own the list it's referencing. It is merely an element and a pointer to the rest of the list. In this case, that is a type definition. It must own the entire thing. And Rust is coming back and saying, whoa, can't do that, because then I'd have to know how big this whole thing is, and I can't check that at compile time. You can always prepend an element to a list. So that's Rust qualm. And think about the reason why that makes sense. All of this shit goes into the compiler at compile time because Rust is going to take out that exact size. It knows how big every type is. Now you're giving it a type, and it doesn't know how big that type is. Now you have a problem. How do you satisfy that problem? You tell it, I want to move the list to the heap. Now I know how big every list is, because I'm defining the list as an I32 and a pointer to the heap. Now you have a linked list. So it's telling you right here the problem and the solution.
So,
The solution is box the list.
so does that mean Rust by default will always store structs or enums into the stack?
It means it always can. It always can. They have to have static size, so yeah. Yeah. All right. So here we have another one, enum messages. And the takeaway here is we've already seen this enum. We've already seen this example. What?
Can you explain? Go back to the box.
Yeah?
The solution. So cons box list.
Cons I32, and then don't own the list. Own the reference to the list. Why does that make a difference? Because you always know how big the reference to the list is. The box of the list doesn't return the list. It owns a reference. It returns a reference that owns the list. The reference to the list always has a known size. It has a fixed size. So the solution works because you now know how big the reference to the list is. And if you have a linked list and you're only looking at one element, you know exactly how big that element is. It's the size of the element. No, let me correct that. Let me correct the terms here. If you're on a linked list, right, and you have one node in the tree, the node in the tree, if it carries the element, will always be the element size plus the pointer size, right? That's what you're telling it. You're telling it you create the element here with I32 in the box of the list.
The box is this smart pointer? Is the smart pointer?
The box with the,
Is that a smart pointer?
that's a smart pointer, yes.
And cons is only one that owns. You can only have ownership of one.
Right,
You can only have one ownership.
that's right.
So that smart pointer is owned by cons.
That's exactly right. It's owned by the type list, which is constructed with cons.
So when you traverse the linked list and you access that smart pointer, you can't own it. You borrow it. When you're traversing the linked list, every time you traverse the next one, you're borrowing the smart pointer.
Yes. Yes. The smart pointer is owned by the list. You are borrowing it when you traverse it. Yes, that's right.
So
Yeah.
you can't mutate it directly. But
That's where we're going with this chapter. I'm not going to read it.
because you're borrowing it.
That's where we're going with this chapter. Yes.
So if the type is box, does that mean if you pass it a list constructor, it's gonna take that, put it on the heap, and then create a reference for it? Is that what it does?
Not the constructor, the thing it constructs, yes.
Yeah.
The thing it constructs is going,
You're constructing it like new or something,
right.
and then it will take that's usually would be on the stack, and we'll put it on the heap instead.
That's exactly right.
Because I was thinking what would be the difference, because they also tell you can also use a reference to a list, like the normal one that we've used before. They tell you on the hint. But I guess if you did that, you would need to construct it, own it somewhere yourself, and then pass a reference.
Yes, it would have a different set of drawbacks. Yeah, that's right. It's awkward to talk about a list where the elements are not owned by the list. I'm not saying it's not a useful structure, but it's awkward. And it doesn't really make sense in this context. But yes, you could come up with something like that. You know, where the list itself is semantically correct and you can add elements to it, but you don't actually own any of the data inside of it. It's just not a very useful structure. But there are some structures like that, you know? Like just FYI, there happens to be some things like that. Like there's one called a B-tree table, I think, is an example of that. Not a B-tree. Yeah, I'm pretty sure in this structure, you have a binary tree which doesn't actually own the data. It owns an index to the leaf in the page. And then the leaf and the page own the data. So this is an example of like a database index, which is exactly that, right? The index doesn't necessarily own the data. It can own to a page on a hard drive or whatever that even owns the data. And if you're talking about a raw database. So this type of thing exists. Like when you create some databases, you say create index, and the index itself doesn't actually own the data. You know, it only owns the index to the data. The data itself isn't owned by the index. In fact, I think that's all databases. All databases that have an index don't actually own the row. Only the clustered index owns the row, right? So this is an example of where your awkward situation is actually true. You could do something probably similar to that, you know?
You should do a Postgres and geek out on it.
Yeah, we could definitely do that, but the only ones who would be geeking out is me and you. Everyone else would be suffering. Yeah. All right. So here we are, computation, the size of a non-recursive type. So the important thing to take away from this enum is that the space for the message value is going to be the variant that needs the most space, right? So if you have an enum and 50 of them are an I32 and one of them is, you know, struct with 30 I32s in there, every time you allocate an instance of that enum, you need to afford the space for the largest variant, right? So yeah, that sucks, but that's just the way it works. Okay, the other downside of the box T is the one that you mentioned, right? Okay, and that is that the box T doesn't get you away from the mutability problems of Rust. So it gives you the ability to create a recursive type, but you have to have a known size. That means in the implementation of a list with a box, you can never push or pop. That's usually not all that useful. Generally, you want a list to grow, right? So here's an example of a list constructed with box, and this is what it looks like. So this is a true linked list here. The difference is that we haven't solved the mutability problem, so we can never push or pop from that list. We have cons 1, and then we're the rest of the list, which is cons 2, and then the rest of the list, cons 3, and the rest of the list. And notice that each one of the lists here on the right-hand side have to be boxed. We'll never get away from that problem. You always have to have the thing that you're constructing a reference to it, right? You always have to have a smart pointer to it in some sort. And that is because we have to have it to be a known size. Okay. The other thing that's kind of interesting here is that smart pointers have the ability to act as regular pointers with the deref trait, right? So we can follow a pointer by its value by dereferencing it, and smart pointers can do the same thing. How do they do the same thing? Well, this part is, I think, in the Rust, and that is the deref trait. So the deref trait, I believe, is implemented on box in Rust, and what that does is it says, when you try to dereference a box, treat the box as if it was a regular pointer. The act of dereferencing something in Rust is implemented with the deref trait, and we're going to see how that works. Okay, they're showing you here that this assert EQ does not work, right? And the reason why this doesn't work is because there's this here, the right-hand side of this, Y, doesn't implement the, that's weird, it should. Wait a second, give me a minute. 5x, yes. Oh, Jesus Christ, okay. That's stupid. This kind of stuff makes it a lot more tricky to teach this book than it needs to be. I'm up here looking at the error, and I'm looking at this code, and I'm wondering why this doesn't work. And I keep saying to myself, that would work. And the actual reason is because that's not the code they're running to generate the error. They came over here, they did the sneaky shit. So that's what I'm missing. This doesn't work, obviously, and that's why we wrote it right up here. So this is saying we're taking y, x, and we're setting it to 5. We're taking y, and we're saying a reference to x. We're asserting that 5 equals x. That's obviously true. Very simple. This one down here, we're not asserting that 5 is the same as y. Why? Because y is a reference. Any other letter would have made that sound better. So because y is a reference, we have to dereference y to check the thing that it's referencing to. 5 equals the thing that y is referencing to, and it passes. Down here, those jokers pulled a fast one on us. If we instead tried to write assert EQ 5y, that would not work. Why? Because now you are asserting that 5 is equal to the references value of 5, which isn't true. The references value is going to be the location in memory it's pointing to. That's not going to be 5. Be very lucky if it was. So that's almost certainly going to fail. And it's going to fail because these two things are of different types, right? And it's going to even tell you that you can't compare an integer with a reference. So you could do that in C. You can actually do that in C. You can say, if the reference equals this value. Rust says, I won't even let you do that. There's such a slim chance that's even remotely what you want. Get out of here. Interestingly, there are some platforms where you do that still, you know? Assert EQ uses the underlying EQ or partial EQ trait. So, so here's what the actual error is. See the trait partial EQ, partial ec, is not implemented for integer and this. So this is the trait called partial ec, and it's comparing two different types. And the Rust problem here is that partial ec for a reference is not implemented for an integer. That's the actual problem. So you could implement that in the Rust standard and it would work like it does in C, but Rust thinks it's so not useful they don't even do that for you. You do this in some actual parts of Rust, you know?
It's not a function,
It's a trait. Partial ec is a trait. If you partial ec is how it's pronounced. Look here. If you do rs partial ec, of course that's not going to work because I'm not doing this right. Partial ec. Okay. Partial ec trait Rust. I need to learn that stupid thing. There we go. This is the trait. So partial ec is implemented on a type, on any type, and you provide it what the right-hand side type is. So this is telling Rust how to compare two different types, which may not even be possible to compare. That's what partial ec return has, right? Okay. Using box T like a reference. So here's where partial ec is implemented. If we look here now, y is not a reference, it's a box. But we can still treat it like a reference, right? Just like we did in the above example, when we use the asterisk to say the value y is pointing to. What they're showing you here is that even though box is a smart pointer, you can treat it like it was a direct reference. Why? Because when you say to Rust, I want to use asterisk on a reference, Rust under the hood says, how does this type that's being referenced implement the deref trait? And the deref trait is implemented for box. So it allows the implementation of box to define how it's dereferenced. And what box is saying is just, here's the behavior to treat me like a reference. I am giving you a reference. I will accept the same syntax as any reference because I implement the deref trait. And now we're going to see how we can implement our own box. Now here's the kicker. This is not how box is actually implemented. So this is a lie. But it's nice because it's simple. We have struct my box, and we say for any type T, I'm defining it, right? So this is a definition of a generic type called my box, and it can accept anything. And what it does is it's constructed with a tuple of just that thing. This could be a my box of an I32, my box of a string, any type, right? Now I'm implementing for all variants of my box, regardless of type, I'm implementing this constructor new. New takes any type you want to provide to it, and it constructs a my box, right? Now we talked about this before. Remember when I said a generic function in Rust will generate a unique copy for every different type of code it can take? That's exactly how that works. So if you only ever use a my box of an I32, Rust will only generate one copy of new. If you use it for 10 different types, Rust will generate 10 different copies of new with 10 different my box definitions. It'll keep them all separate, but that's how Rust generates code depending on how it's used. And the advantage of that is it's as fast as any native code. You couldn't handwrite something faster, right? So that's how generics work. That process, the big long word we use, which comes from C++, was monomorphization. If anyone remembers that or remembers that part of it. So here we have x equals 5, and we say y equals my box, and we're giving it new x. And we're constructing this box that we just created with this value, this I32 5, right? Now we're doing assert equals 5 and x, assert equals 5, and the dereference value of y. And it's complaining. It says this doesn't work. Now why did it work for box and it doesn't work for my box? That's the question. We implemented box, and ours doesn't do the same trick. The reason why ours doesn't do the same trick is because we did not implement the deref trait. We're getting this error here. Now, right off the get-go, I would say that is a shitty error. It's a shitty error because the other error that we got actually told us what we needed to do. You need to implement partial ec for an integer reference on an integer. That was the error that we got. This error, I would critique it because it's not telling us what we have to do. Just telling us the problem. It cannot be dereferenced. A better error, in my opinion, was my box doesn't implement the deref trait. Then it's telling you what you have to do, implement the deref trait.
So does my box gets allocated on the heap as well, even if you start with the basic type?
Yes.
That is the million-dollar question, and the answer to that is no, not yes. Yes, we're going to overlook that. I don't think it actually says that here. Let me see that here. Yeah.
In the stack, they never tell me this inside the function. You can't read the functions.
It doesn't leave the function. My box is returned as ownership. What do you mean? It's returning a copy of my box. The question isn't whether or not it's returning an owned copy of my box. That it clearly is doing. The question is, where does that copy live, on the stack or the heap? And the answer would be, you can locate that on the stack, right? This doesn't go into that because now we're in the crazy land, right?
So if you have two separate threads accessing this smart pointer, but they're actually outside of the function scope that was created.
At this point, it's not a smart pointer. At this point, this is just a struct called myBox, right? We haven't implemented the deref trait yet. This is not a pointer. And even after we implement the deref trait, it will not be a pointer. Why? Well, it will not be a pointer to the heap. Why? Because the code that makes box allocated on the heap that's in C. That's in C. That's not in Rust. We use box to tell Rust allocate this on the heap. You can't use Rust to tell Rust to allocate something on the heap, as far as I know. Way above my pay grade. I've never implemented an actual copy of real box, but I think that you are asking a very good question. So hats off, you're obviously paying attention to this. I think this is an oversight, and it's because this is supposed to show you the simplicity of implementing a smart pointer. And the reason why they want to teach you about the simplicity of implementing a smart pointer is because we're going to be talking about a bunch of them. The fact that the one that we're implementing here isn't allocated on the heap, even though it would lead you to believe it's allocated on the heap, is something the book overlooks and just hopes you don't pay attention to that. I don't see anything in here that actually even says the word heap. Yeah, there's nothing. So, yes. Good catch. Good catch. That's going on the stack. All right. Treating a type like a reference, it doesn't matter at all for this, but it's an interesting catch. Treating a type like a reference by implementing the deref trait. So now we have this type that we've created called myBox, and now we're showing you effectively how simple it is to make it a pointer. So now we say here this deref works for all copies of myBox, and what it's going to return is whatever the type the box is. So this syntax here, impl t deref for myBox t, type target equals t, this is useful, and you'll see this a lot. This is creating, I believe the right word for that is an associated type, target inside. And that target gives you a name of whatever you are wrapping, right? So the target here is saying it's the type t. And now we have a reference for it. So now when you call deref on a reference to self, it is going to return to you not a reference to self, but a reference to a target. It is unwrapping that type. And that is returning self.0. And then there we go. And now you'll actually see what happens. Whenever you type in asterisk, what it's actually doing is this. It's not saying what is the value that I am. It's saying what is the value of deref. And that's why there's an implicit call to deref whenever you use asterisk. And now you actually have the ability to dereference something without using asterisk at all. And we'll talk about some of that in a second. So Rust substitutes the asterisk operator with a call to deref method, and then the plain dereferences it, so we don't have to think about whether or not we need to call the deref method. So this here gets substituted with this. Yeah. Okay. This is an interesting point there too. The question here is, why doesn't deref just return the actual value? And the answer is very evident with that explanation. The reason why it doesn't return the actual value is because then it would have to move it out of self. So something owns the value, and just because you're looking for a reference to it doesn't mean you want to accept ownership of it. So we're still letting the struct own the value, and that's why it looks a little awkward when we explain what's happening. But I said this a lot, Rust has a lot of layers of voodoo as you scrape it back. When you use that question mark, it's very transparent what's happening. It's using effectively a try macro under the hood, right? And that macro is not too complex. So I'm still saying we just use the question mark and we forget about how it's implemented. But if you actually read how it's implemented, it's pretty straightforward. There's less magic behind a lot of Rust implementation than you'd find in other languages. And it's explaining to you some of the voodoo here. Implicit deref conversion coercions with functions and methods. So here what we're doing is we have hello, and it's taking a string reference, and I am printing it out right here. And it's telling you that there's an implicit coercion from that string slice. Yeah. Okay, so the catch here is, this is interesting. This is what they're showing you. It's on both of them. This isn't shocking at all. This is actually really boring, and we've already talked about this a lot. Down here, what we're doing is we're declaring function main, and we're saying now, we know that the top will take any string slice, but now we're declaring my box, and we're saying string from Rust. So now we don't actually have a string that's getting silently coerced to a string slice. We have a my box of a string, right? Now, a string is always located on the heap anyway. Yeah, pretty sure that that's the case. So a string is always located on the heap anyway. A my box of the string is also going to be located on the heap by proxy of that. So in this case, this would be one of those cases where my box is on the heap. It's on the heap by proxy of string. It's owning a string. Therefore, that's where the data is at.
Wait, so my box, will it be storing the fact pointer? So now the pointer itself is on the heap, and that pointer will be pointing to a different place on the heap?
No, no. So get this. String always has to be on the heap. Yes or no?
Yes.
Yes. My box is going to have a pointer, right? The pointer, as made a reference to earlier, is not going to be on the heap, right? So my box is going to effectively store, likely on the stack, a pointer to a location that just so happens to be on the heap. Why is it on the heap? Because string is on the heap. So if you had a pointer to an I32, then it's likely that the pointer and the I32 are on the stack, right? Now that you have you're using an object, a struct that's already on the heap, you're going to be having a pointer on the stack to a struct on the heap, which is how box would otherwise work. Box doesn't return to you the pointer on the heap. It allocates the thing it's pointing to and moves it to the heap and gives you a pointer which can be on the stack.
Yeah, but a string is a fact pointer, right? Or
No.
What if your function returns my box? And so when you return, you leave the function scope.
Then it doesn't make a difference. You're confusing ownership with reference, right? You're giving it an owned fat pointer. So the owned fat pointer you're giving it will totally be fine on someone else's stack.
Wait,
But the okay, if you return this thing, right?
Yeah.
You return a fact pointer to my box. But you say the pointer inside the my box is now outside outside the function scope. When you
my
return the
understanding is that a string like this would give you a pointer and a length and a size. Isn't that correct? Like without the box.
It will give you a pointer and a length, right? Yes.
Now if you box it,
And
you box it.
it'll give you a pointer, a length, and a capacity. It's a string. It has all three, right?
When you box,
when you return it, what happens to the pointer?
so you're saying you're moving to the heap. Why are you moving to the heap? The length, capacity, and the pointer, or see what I mean?
Yes. Okay. I see what you mean. You are not moving that to the heap. Why are you not moving that to the heap? Because my box doesn't move things to the heap. This is an error that was already pointed out. So get rid of this idea that my box is moving it to the heap.
I thought that was using box, not my box.
There you go. If it was using my box, yes. Then it would move the
box.
If it was, yes, I'm sorry. Yes, good catch. And thank you for being assertive. You're right this time. If it was using box, the fat pointer would go to the heap. You would get a new pointer to that location in the heap where the fat pointer is. Which is what you're thinking, but no. Because we're using my box, there is no implementation way for them to send that to the heap without using box internally. They chose not to use it because it would be very silly, and it would only catch this case. So they did not do that. Therefore, my box is likely just on the stack, almost certainly, unless I'm missing something, which I could be. I haven't examined this code more than a minute, but my box is likely going to be on the stack. It's going to have the fat pointer to the location on the heap. Why is it on the heap? Because all strings are on the heap.
That pointer is my box.
No, the fat pointer is the string. The string has a location on the heap. The fat pointer has that pointer to the heap, the length and the capacity. Remember, we covered this. The location here, look. Am I making this up? I'm not making this up. No.
And that one said storing UTF-8 encoded text bits.
I didn't think so. I thought it was way before that. Either that or time is just moving slow.
That's fine. That's not the question. So let's say you have a function that creates my box and then returns it. The calling function that called the function that created my box, it still has access to it in the stack.
Give me 1 second here. I want to see something here. References and borrowing, the slice type. There we go. There we go. Okay. There we go. S is the string. The string has three things: the pointer to the heap, the length, and the capacity. That's what the string has, right? That's the string. So S is the string here, and we are creating it with string from hello. It has the pointer, the length, and the capacity to the location on the heap. The S here is what you're calling the fat pointer, which is the right name for it. When we create a string, the data is stored on the heap. We now have this type, this fat pointer, and we are wrapping it in my box. It just so happens to be the type is pointing to the heap. This fat pointer we are wrapping in my box needn't be on the heap, and it isn't, because my box doesn't put things on the heap. Only box puts things on the heap. All right. Are we on the same page now?
Yeah, okay. So what happens if you create this and now you return it? Return it.
Then you will be giving the S. Just imagine what happens normally. Can a function normally return a string in Rust?
Yes.
It can. Why? because it is giving ownership of the fat pointer to the thing that called it. That's what returning a string means in Rust. When you return a string in Rust, the string doesn't move. The fat pointer owns the string. The fat pointer moves. What does move mean? Moves means that ownership has changed from one location to another. That's what moving in Rust means. When s, this fat pointer, is returned from a function, the string stays there. The s, the fat pointer, is returned. Now something else owns that fat pointer, right? If nothing owns that fat pointer, then what happens? The string is dropped, right? Now here's the catch. If a function returns a string and nothing saves the value of the function, is the string dropped? Immediately. That's what happens, dropped immediately. So what will Rust say in that case? It'll say, you have not used the return value of the function. Assign the return value to something. And you'll say, fuck, what should I assign it to? And this is where Rust will suggest to you the underscore. The underscore will then own the string. That's what it's there for. It's there because Rust doesn't want it to be the common thing that you call functions that are returning something and then they just mysteriously stick around. So when you call something and it returns it, you decide what you want to do right away. This thing is going to own the return value. And if you don't want it to own the return value, create a scope around it and let it drop. But you got to do something with it, right? OK. Does that answer all the questions?
Yeah, I just forgot. If you return something, it stays on stuff. That's all.
Yeah, the ownership, and we had this conversation earlier. This was, I think, the most heated question we've had in the whole class. You remember this? Then remember the most heated question we had in the whole class? The book is wrong. You remember that? It was a great question. We had a question that went on for a while, and the book was certainly wrong, and he wouldn't, it was some insistence. If you return something and it is moved, that doesn't actually mean it is moved as far as talking about the bytes. It means the ownership has moved. The ownership is a mental construct. We say the thing has moved, and it may move, but it also may not move. Because Rust may realize that thing needn't move. You have returned a pointer to that thing. Why the fuck would I want to actually move it? Right? And it can, as a compiler optimization, keep everything in the same place, even the fat pointer. It has the ability to do all of that. It has that levity. It's about me conceptually explaining to you what happens, not me being dead on about it. So if a function returns a string, nothing may move. We may think about it as moving ownership, changing ownership to the other thing. OK. Are we ready? Let's go back. OK, so now we have this my box. We put the string Rust on it, and we are calling hello now with my box. And this works. And why does it work? Well, wait. Yeah. It works because we implemented deref coercion. Now, this is again where I really think the book is way off in the fucking weeds. But if there was no deref coercion, what would the language look like? That's a very silly question. We could play that with everything. If there was no deref coercion, this is what we would do. We would say, let me pop that up a little bit higher. We would say explicitly dereference m, then take a slice from it, and the slice with ... is Rust's way of saying, I want a slice to the entire thing, which basically means give me a fat pointer and drop the capacity. It's a read-only fat pointer with a length and a location on the heap. That's what that slice syntax does. And you'll see that in some places. In fact, I forget that syntax sometimes, and other people have to remind me of that's how Rust does it. Because I want it to just work without it. I want the string to, in all cases, have like a conversion where I can go : convert to string slice or something like that. But this is the actual syntax. This is how they do it in Rust. So you do this dereference of m, then you say you want a slice to everything, give me all of the contents of that string, and then I want to take a reference to that, right? So now I have a string slice, a reference to a string slice. And if I didn't have the deref coercion, I'd have to write all that stuff. But because I have it, deref coercion will first tell my box, return to me a reference to the thing you carry. And then that thing will come back and it'll say, I have a string. And then Rust will say, return to me a reference to the string, or return to me the reference to the string. And then Rust will say, what kind of reference do you want? And then it'll say, you're calling it in a string slice, so I'll take a string slice reference to it. And that's how that actually happens. So you see multiple different deref calls in this syntax here. The first is my box, right? What does my box have? It has a reference to a string. So deref is going to get us the string, the string reference. Now we're going to say, I want to get to this, and what do I want? Well, hello is defined not to take a string. It's defined to take a string slice, and deref will answer that call. It'll get us the actual string slice from the owned string. And there's the explanation. Star m dereferences my box string into a string. Then the ampersand and the dot dot take a string slice of the string that is equal to the whole length to match the signature of hello. This code without deref coercions is hard to read and understand with all these symbols involved. Looks a little bit like Perl. Deref coercions allow Rust to handle these conversions for us automatically. And that's really the kicker here, that this ability to recursively call deref or asref as you need it to get from one type to another and to get to the type underneath it. All this stuff happens for you, and it just does what you want. And it's also type safe. If Rust can do it with 100% success, it does it, knowing that's exactly what you want. And if there's any chance that's not what you want or that it's unsafe, it simply fails and requires you to be more explicit. And by the way, this is one of my failures too with C. There's a great example about how no one can read C pointers. And even if you use C a lot and you think you can read C pointers, you can easily create an example where it's impossible to read C pointers. Remarkably difficult. Would take even a pro minutes of looking at it to figure out what the fuck's going on. Because things can return references, and then you can dereference them, and then sometimes you can dereference them twice because you have pointers to pointers, and it gets really crazy how you pick, am I looking at that thing which is a reference, or this prefix before it which is telling me what to do?
Compilers, C compilers are better at warning you.
Where is it? Here. I'm trying to find an example of like an unreadable C pointer. There's definitely some really good ones that are remarkably short.
There's just historical reference. There are some in the SQLite source code, and the reason they're so ugly is sort of backwards compatibility with machines with weird pointer behaviors.
Yeah, I'll look this up later, but this could be fun.
Modern C source codes, I mean recent C source codes, they don't have these weird things because they don't have to worry about legacy hardware. You find them in like zlib,
Yeah.
libz code because that's to be backwards compatible. So many weird stuff.
All right, how to deref coercion interacts with mutability. Let's hit this up. So the key here is that there's two different forms there's two different deref traits. There's deref and deref mute, right? And the rule is very simple. When you want a mutable pointer, it's deref mute. Otherwise, it's deref. Why is that the case? Because not every pointer can produce a mutable pointer. Not every type can produce a mutable pointer, I would say that, right? So, for instance, box may not implement a mutable pointer. It could be in a read-only form of memory or something of that sort, right? You can get into those situations where you don't have a mutable pointer and no one can have it, right? In those types of cases, you would not implement deref mute. You may implement deref. You can dereference this to see what's stored there, but you cannot write to it. I don't have to go much more into that. Running code to clean up with a drop trait. A drop trait is very simple. All that Rust needs to do to drop code is simply have a lack of ownership. But you can have things trigger when it drops code too. So here's an example of you creating a drop trait that implements an additional logging feature where it tells you this is now being dropped. And to do this, all we're doing is implementing drop for that type. Impl drop for custom smart pointer, right? And you can write whatever code you want there. It's just, think of it like a mixture of a drop trait and a deconstructor, you know? Whatever code you want to put in there, you can throw in there. And there are really awkward rules too about the way Rust drops things. So if you have structs that own structs, the inner structs get dropped before the outer structs, which makes sense, but it could be producing some weird dropping rules for you if you're not expecting that. Just be aware that your inner struct will trigger drop first. So D was dropped before C. Yeah, like this kind of stuff too. D gets dropped before C because they're dropped in reverse order. So effectively, the stack is cleaning things up by unwinding, and the things that are declared first are at the bottom of the stack. It grows up. So it's essentially moving in the opposite direction. And that's how that works.
Can you go back to the
Which one?
the one that you were just looking at?
This? Let me get rid of this thing too. Unneeded. Is that what you want?
Yeah. So but you're not using C anymore. So wouldn't the compiler be smart enough to realize that and drop it before even assigning D?
I don't understand the question. You're not using C
You're
anymore.
assigning C equal to your smart pointer, and then you're assigning D, but you never use C. So wouldn't the Rust compiler be able to drop it before even assigning D?
That's a good question. So the question is, why does C live long enough to where D is hit? And the answer to that is, it's not guaranteed to live long enough to when that's hit. However, it is guaranteed to drop in a specific order.
So in that case, I guess the compiler decided it was faster to drop both of them at the end.
You get the same performance if you ran it in debug and release.
I'm trying to think whether or not I want to comment on that or just simply say I don't know and leave that alone. I'm going to say I don't know on that one and leave that one alone.
Okay.
I'm going to say that's also a really good observation. And I will say this, the Rust compiler does not guarantee C will live as long as D. However, it is making guarantees about when it's dropped. So that would be a really fantastic question for Stack Overflow. Let someone smarter than me answer that one. I don't know.
You can try compiling it in debug and release and see if they pay.
Yeah, no, that would be a really good Stack Overflow question. I don't know the answer to that. I don't know how, unless it's guaranteeing that C and D live until the end of the scope, and I clearly don't believe that to be true. And I think that could easily be shown to be true in the event you have a mutable reference, which goes away beforehand. Yeah, and the way I would ask that is I would say, does Rust guarantee that C will live until the end of main? Or can Rust free C when it no longer is in use? Right? And there's your code. Yeah, good one.
But I didn't get what the code is trying to demonstrate there.
The code is trying to demonstrate that we have C declared and then we have D declared, and that they are dropped in opposite order, right? So we say dropping custom pointer with data, other stuff, and then my stuff. See the order, other stuff before my stuff? Other stuff is D. This is C. So they're declared this first and then this, but they're dropped in the reverse order. This gets dropped and then this. So the question is, if C isn't guaranteed to live until the end of main, then how come the drop function gets called after D? C doesn't even have to live past this line. Why? Because nothing is referencing it. So my intuition is that the book is wrong. The reason why I don't want to go there is because there's a good chance I'm wrong too. I feel much less confident about this question than your last question. So my assumption is that in order for this to be valid, a valid statement, they should have put C and D in the println statement. They should have said println C, D, because then they're showing you that C and D both have to live until the same point, and they're showing you how they will drop. But without that assurance, my assumption is the book is simply wrong, and this is an error. And I would want someone smarter than me to validate that. My assumption is you are right, C can stop living right here. And Russ could decide to drop it right here. Then you would see the drop message, then D would get allocated, then D would get dropped. And those are my assumptions, that's my gut feeling. I don't place much confidence in it though, this time. All right. But yes, good question.
Maybe it saw the drop trait, so it assumes it has, because it has that trait, then it has to live with you.
It's possible, but I want someone smarter than me to say that. I have no idea. I have no reason to believe that. I have never dug into those kind of, I've never dug into that corner of the closet. I would, yeah, I don't think so. I think it's just a problem in the book. But again, this gets down to the point, like, how much of this shit do we really want the book to explain? I'm making the argument the whole time reading through the book that it's going too far into details on a lot of things. And then people ask me these questions where I'm like, well, now I know how all this shit is here, you know?
We're going all down.
Yeah. Yeah. I like it. It keeps people engaged anyway. So, I hope people are paying attention like that. Dropping a value early with std mem drop. Okay, so we can force something to be dropped. We can't use .drop for it. Why? It's an arbitrary rule of Rust. So Rust's basic rule is that if you call c.drop, it looks like it's a method, and it doesn't like that. So you have to explicitly call std mem drop. If you try to call drop without it, like this, it'll say explicit destructor calls are not allowed. Consider using the drop function, drop C. That should probably say std mem drop instead, to keep it simple, show people where it's from. But the reason there is because if you just call c.drop, Rust will still internally try to call drop. So that's the reason.
Yeah, anything that has a drop trait will have a side effect. The compiler will assume, so we'll have to keep it until the end.
Well, if you use std mem drop, not. See, the thing here is that even if you use std mem drop, yeah, okay, because std mem drop is taking
sees a potential side effect, so it would.
Yeah, std mem drop is taking ownership, so it semantically makes sense for Rust behavior to change because something else has taken ownership. If you called c.drop, nothing would be taking ownership of it. Therefore, it doesn't make sense. No, that doesn't make sense because drop is still calling under the hood. It's taking ownership. It's owning self. That doesn't make sense. No. Another real good question would be, why the fuck is this the case? That doesn't. I think that this is just Rust special casing things, more than an actual error. The book is actually hitting on something.
I actually tried it. It is drop after the print statement, which is interesting.
In which case?
It's doing it like it says in the book.
Oh. Well, that doesn't shock me. It can't drop before the print statement because the print statement's going to read it. So that's obvious. It's going to have to drop after the print statement. Which one? I'll go up.
No, that one.
This one?
It's running in that order.
Yeah, but I'm saying this is obviously the case, right? It must run after the print statement because the print statement, the print statement's not referencing it. Therefore, the question is, why is it running after the print statement? Yes.
The drop thing is a hook. You can think of it as a hook. Anything that has a hook, then you have to keep it running. You can't ignore it.
So far.
No, someone smarter than me has to explain that one. I don't have an answer and I don't have a comment on it.
Like the garbage collector, right? It sees that there's something, there's a hook.
There's no garbage collector here.
Forget that. Just at the machine level, right? Well,
I don't agree. I understand all the words you're using. I don't think it has any relevance here. It doesn't have, in my opinion, it shouldn't have any relevance. I don't understand what's going on, but I don't understand that explanation.
Like in JavaScript, you attach an event listener to something, right?
Yeah, but this is an event listener. This is all.
Sort of drop is sort of like an event listener. You have to fire this event after it leaves scope, and the compiler sees that sees this.
That is
It sees
that is not true with my understanding. I'm not saying you're wrong. I'm saying that is not my understanding. It'd be a very fundamental misunderstanding if that was the case.
That means the compiler is free to ignore any kind of is free to ignore drop at will when it falls out of scope.
I didn't say that. I said it's free to call drop before the end of the scope.
Oh, but it's not required to.
Right, sure.
Oh,
So I'm saying the question is, how is the book guaranteeing that this is the
so
case?
drop is not guaranteed to run when it leaves scope.
I don't think drop is guaranteed to run when you leave scope. I think it can run any time before the end of the scope.
Oh, okay.
Like, for instance, look at C and D right here. This is the question, very simple. Nothing is referencing C after this line right here, right?
But you could.
That's the last line that's referencing C. Yes?
But you could program it.
That's the last line that's referencing C. Okay, so the question is, if that's the last line that's referencing C, C doesn't need to live longer than that line, right? And because C doesn't need to live longer than that line, and because lifetimes are now line specific, they are not simply function specific or scope specific, because scope, this is part of, we even went through this, right? Rust, we called it here, lifetime lines rust. Let's find the name here. Does anyone remember what this was called? The line lifetimes in Rust? Or
Can you just look up the documentation for drop? Say where it's required. It forces the compiler to wait until out of scope, or it's not required.
the drop trait has only one method, drop, which is called automatically when an object goes out of
So
scope.
it is required to run, always run.
There's no disputing that it's required to run. And there's no disputing that it's required to run when the object goes out of scope. The question is, can it run before the object goes out of scope when it no longer needs to live? That's the question.
So this one's not referencing it either.
Right. So let me tell you how I would ask this in the event that we're interested. Lifetime scoping. I just forget the name of this. The lifetimes used to be scoped to functions, and now they're not. There's a new thing here that it's not new, it's probably 2018. Here we go. Here. Technically out of scope, however, it leads the instructor. One way to convince the compiler X is no longer to use the drop function.
Yeah, so I just run a few different versions of it.
Yeah.
And it seems to only be dropping it, like popping off the stack the things within that scope at the end of the scope. It's not doing it when it's not used.
Okay. Okay, that's interesting. This is how the ownership rules work though, right? This is how it describes it. It says, the bar checker always tries to minimize the extent of a lifetime, so it will likely sugar the following to, and we see the let X, let Y, let Z. We went through this in the Rust book. I forget what chapter it was on. That's it creating artificial scoping to show you this, right? It's saying the scope of tick A encompasses everything. The scope of tick B encompasses Y and Z. The scope of tick C encompasses just Z, right? We have those 3 different nested scopes like that. And the reason why they're showing you that is because the reason why they're showing you that is because, how would I say this? So x equals 0, y equals the lifetime of z, x equals the lifetime of y. Anyway, let's loop back to this. I don't want to waste any more time on it. This is an interesting question though. I'll try to come up with some examples or try to figure out a better answer for you. I don't have a better answer. Dropping a value early with stdmem drop. This is very simple. You call stdmem drop, you give it the variable name. It transfers ownership and the thing gets dropped. I don't know why Rust doesn't let us call drop explicitly. This is another really good question. I don't have an answer for this. Why don't I have an answer? Because a method in Rust can take ownership of self. And if it can take ownership of self, it's effectively dropping it. So drop is implemented such that it takes ownership. Dot drop is calling that implementation in the trait. It is taking ownership of it. So the fact that you can't call drop by doing dot drop seems to me like it's a Rust thing, more like a special casing rule. std memdrop doesn't trigger a double free because someone wrote code in there specific to std memdrop. They could have written that same code in there specific to calling it with dot drop. They chose not to. That's my guess. I think it's arbitrary. Yeah, so this doesn't make sense to me either. In fact, if no one's going to ask these fucking questions on Stack Overflow, I'll ask them. Because I think these are really good questions about the book. Very niche questions, but they're all good questions. So now we're dropping it. We say custom smart pointer created, dropping custom smart pointer with data, some data, custom smart pointer drop before the end of the main. And that's what we're doing here. So we create it here. Then we print this line, then we drop it, and then we do this, print the other line. And that's what it's showing us. The drop happens right here. RCT, the reference counted smart pointer. Okay, finally we're into the guts of this thing, and I think we've been moving dog shit slow. So let's pick this up. RCT is the reference counted smart pointer. Here's how that works. Now I have a type B, and you'll notice that it not just has the node and the pointer, indicated by the line, but there is also, we're going to put a counter inside of it. So we have this enum list. We've already seen this before. And the list is cons, I32 a box list, and nil. This allows us to create a list of undefined length, right? And it allows us to create a list of undefined length because every list we create has a defined size. It has one element and the smart pointer. So now we're going to see here that we cannot create, okay. So now what we're showing is we have this list we create up here with A. It's right here. This works. And then we're trying to create list B and list C that prepend different values to A. So list B has a 3 and the value of A. List C has a 4 and then the value of A, right? So can we take A and can we create 2 lists with A? We cannot do that. Why? Because both B and C cannot own A. And this form of a list requires ownership. So how do we get around it? We can use the RC. And if we change list definition now to cons I32 RC list, it'll work. Why? Because an RC is a smart pointer with a counter on it. So now the counter tells you how many copies are owned. The assumption isn't just one copy owns it. You can have multiple different copies that are owning it or sharing it, right? Now it's important to say that RC is not mutable, doesn't allow any mutability. So ownership in this context doesn't mean you can mutate it, right? So we have another trick yet up our sleeve. We haven't gotten there yet. We'll see it in a second. But now this allows us to say we want a reference counted list for A, right? And it's cons 5, and then another reference counted list, cons 10, and then nil. So we have a list of 5, 10, and then the empty type, right? That's how the list is created. And then B is going to be cons 3 and the RC, and C is going to be cons 4 and the RC. This works. Notice we get to this reference counted list by using RC clone. What does RC clone do? RC clone takes the counter internal on that reference. RC is reference counted. When you clone it, it doesn't just create another copy. We said this earlier in the chapter and didn't go over much of what it meant. Clone does not mean a byte for byte copy. It can do other things. When you clone a reference counted smart pointer, it increases the smart pointer, the counter inside of it, right? So an RC is a counted smart pointer. When you clone it, it increases the counter and does what cloning any other pointer would do. Interestingly, this is how Perl works under the hood. So Perl uses reference counting everywhere. So everything in Perl is reference counted, and this is how you could represent anything in Perl. You know, you could represent it with reference counting like that.
How is it mutating incrementing the counter?
What's up?
How is it mutating / incrementing the counter?
Okay, that's an interesting question. How is it mutating, incrementing, and counter? The thing is, we have made broad statements such as you cannot have an integer owned and incremented by multiple different things at the same time, because only the owner can increment it, right? It is not exactly true in the case of an RC. Why? Because there is a primitive type which can be incremented, and it's not actually true. Yeah, we can get into it. Yeah, there's a little bit more to it. Okay, so RC increments it when you call clone. It increments the implicit the counter for the reference counted pointer. Cloning an RC increases the reference count. Here's an example of it. Here we're saying A is this reference counted pointer to this thing, and then we're saying inside of it we have another list here, which is a reference counted thing like this. This is A, and then B, we're cloning A here. And what we're showing you is the count after creating it. So there's a strong count and a weak count. So the strong count and then the reference of A tells us how many times we've incremented it. Tells us how many outstanding references we have to it, right? So Rust has effectively the ability to decide when things are dropped in compile time. It does that with this notion of borrowing and lifetimes and ownership. It determines when things get dropped. With RC, you are turning that functionality off. You're saying we can no longer do this in compile time. We're going to do this in runtime. And the runtime way of doing it is this internal counter. It goes up every time you use it. It goes down every time it's freed or dropped. And then when it gets to 0, then Rust says, I'm at 0, you can drop and deallocate that memory, right? So what normally would have happened in compile time gets pushed off to runtime. And it works because RC is safe. Okay. So the RC thing is pretty simple. Counter goes up every time you clone it, goes down every time it falls out of scope. When it gets to 0, the thing gets free. That doesn't get you what you want generally, because what you generally want is that plus the ability to change it, whatever's inside of it. And I already said that RC doesn't allow you to change things, right? What does allow you to change things is ref cell. So ref cell under the hood allows you to run borrow mute on things and get a mutable pointer. So here's an example of something that won't work. x equals 5, y equals a mutable reference to x, right? That will not work. Why won't that work? Because x is not mutable. So you cannot borrow a mutable version to an immutable variable. Doesn't work. And that's what it tells you right down there. It cannot borrow it as mutable. What you can do, though, is well, I don't, it's building it up here. Talking about wireless stuff doesn't work. This is getting into mocking. This is going way off task. Here. What you can do, though, is do this ref cell component right here. So this is the first example, I think, of ref cell that they've used. Let me make sure that I haven't missed anything, because we jumped pretty far down. Yeah. No, that's the first time. I'm kind of shocked that they don't show any examples of it until this. But this is where it's at. So mock messenger in this case, which we've seen, they show you other examples of it not working. We're going to now solve the problem with ref cell. Sent messages here has ref cell vector string, right? Now we have a vector that is owned by the mock messenger that we can mutate. And how do we mutate it? We mutate it by calling this, borrow mute. That's all there is to it. This borrows a mutable copy, and you can have one of them. The RC will allow it, and you can now push to it. So borrow mute is going to return the mutable reference, and now you can call dot push on it. So this allows you to have one type here that is not mutable, right? This struct mock messenger is not mutable, and you can still, through interior mutability, mutate it. And this idea of interior mutability is everywhere. Like if you take, let's take Python, for example, and we'll show you it in a different language. If I say a equals, let's say here, foo equals 1, 2, 3. Bar equals, let's say here, now I have hello 1, 2, 3. Now what you should notice here is if I do bar.0, what is it?
Bracket 0.
Yeah, bar.0 I get hello, but I can't say bar.0 equals foo. Why? Because it doesn't support assignment, right? I can't assign to this tuple. It's an immutable type. But it does still have immutable, it does still have interior mutability because of foo. So I can say foo equals 1, 2, 3. I can say foo dot, oh, what is it? It's foo dot append. Now I have 1, 2, 3, 4, 5, and if I call right now on it, bar, I get hello 1, 2, 3, 4, 5. So in this case here, you're looking at Python, right? And I've shown you that when I did it up here, foo 1, 2, 3, foo dot push, foo dot append, this worked. And now I have 1, 2, 3, 4, 5. And bar mysteriously changed. Bar is a tuple. It's supposed to be immutable, but it has a list on it, and that has interior mutability. So this is how it manifests in other languages. So this is just showing you how we get at this effect. We get at this effect in Rust by using ref cell. Ref cell gives us the ability to mutate something, not through compile time guarantees like immutable references and mutable references in compile time, but through borrow mute on the reference counter. And then it determines this. When creating immutable and mutable references, we use the ampersand and ampersand mute syntax respectively. With ref cell, we use borrow and borrow mute methods, which are part of the safe API that belongs to ref cell. The borrow method returns the smart pointer type reft, and borrow mute returns the smart pointer type ref mute. We already saw this. It's the same thing with deref and deref mute, which we saw earlier. There's a different trait for implementing, getting a mutable reference, right? Both of these types implement deref, so we can treat them like regular references. The ref cell T keeps track of how many ref T's and ref mu T smart pointers are currently active. Every time we call borrow, the ref cell T increases its count of how many immutable borrows are active. When a ref T goes out of scope, the count of the immutable borrows goes down by 1. Just like the compile time borrowing rules, ref cell T lets us have as many immutable borrows or 1 mutable borrow at a time. When we try to violate these rules, rather than getting a compiler error, as we would with references, the implementation of ref cell will panic at runtime, right? So we're getting a panic when we try to violate these errors. Now, it's kind of interesting because ref cell is written in pure Rust, unlike Box, which is fun, because that means I can actually show you how it works, right? And this is nice. And that's not what I want. This is what I want. So if I go down here and we do source, we can actually see it. This is the implementation of ref cell. And what you want here is I think it's simple. There we go. FN borrow mute. So borrow mute calls try borrow mute, right? And I just wanted to show you a little bit about what this looks like. What try borrow mute does is it says there's self borrow and it's matching, right? So it says, I actually, before I went here, I imagined this was substantially easier than it is. I thought it was just going to say if it has 0, you can get a mutable borrow. If it has not 0, you can get an immutable borrow only. But it says here, try borrow mute matches borrow ref mute new, self borrow, and if that is some B, yeah, I don't know. I'm going to ignore this. Ignore this. This was a mistake. I'm going to read that code myself. I'm not going to try to make sense of that live. That's way more complex than I thought. That's weird how you do those things. So like, yeah, my concept of it was very simple. There's a counter in the reference counted type, and I imagined that counter was simply being checked for 0. And if it was 0, you got a mutable reference. And if it wasn't, then you can only get an immutable reference. That's what I was expecting to see. And then I pulled it up live, and I was like, holy shit. You know, what in the hell's going on there? Why is that so complex? This is going to take me a long time to explain it. Like there's this thing here that I saw called phantom data, right? And yeah, right here. Yeah, I'm not, that is a whole rat's nest. I'm staying out of it right now. Okay. So there's this implementation of Messenger, and they're showing you here how they try to execute 2 borrow mutes, and this is throwing the error, right? We created a variable called oneBorrow for ref mute T smart pointer returned from borrow mute. Then we created another mutable borrow in the same way. This makes 2 mutable references in the same scope, which isn't allowed. I was just trying to show you how that was implemented. It was an honest mistake. Notice that the code panicked with the following message, already borrowed, borrow mute error. And the funny thing is, if you go over here, already borrowed, borrow mute error, that is this error right here. So they're actually looking at the same file that we are. I just don't want to explain how they're getting there. It was way more complex than I thought. Choosing to catch borrowing errors at runtime rather than at compile time, as we've already done, means you'd potentially be finding bugs in your code later in the development process. That's always a point. The second you deviate from catching all of your bugs in compile time and you do this runtime stuff, you now have to write tests and you have to rely on your tests because the compiler is all hands off at this. And in fact, this even gets down to this concept in Rust, which are basically axioms and foundations, you know? Rust gives you a type called unsafe cell. You can do whatever you want with it. It is unsafe. Implementing something on unsafe cell requires you to use unsafe code in Rust. We haven't really covered that. Ref cell is implemented on top of unsafe cell. The core of ref cell is unsafe. It just so happens to be that you can only access this unsafe cell through the safe mechanism. And that's where the sanitation process comes in, because there is a proof for showing that ref cell is safe as it's used. It's very simple, you know. When you can't free it before it's 0, and you can only free it when it's 0 once. That's what you want to prove. So that's easy to show. Having multiple owners of mutable data by combining RC and ref cell. Okay, so here's how we do it. We can create a reference counted ref cell. This means we can have multiple copies of ref cell, and they can have borrow mute. And there are implications of this too, right? So here's how it works. Ref cell new 5. Now we do A equals RC new, cons, RC clone, RC new. So now we're cloning to increment the ref cell, and we are calling RC new to create a new reference counted piece. But now you can see here that we have the ability to deref it as a borrow mutable and add to it 10, right? And then when we do this, it will affect all of the lists. So we are taking to this here value.borrowMute right here, right? And we are changing this value by adding 10 to it. And you will see this appear in all of these different lists. Why? Because this one implements value, and these two implement that one. So we change it in one place, and it reflects it in 3. So this gets us what we want, which is like a mutable reference counted list, right? Linked list. This is how we do it. Now, there are drawbacks to this approach too. So you may say, okay, this is a panacea. This does what we want. It has, we can have mutable copies all over the place again, and we can do it in a safe fashion, and Rust will check it all in runtime. Okay, that is tremendously powerful and good. There are some downsides to it. This only works on single-threaded applications. There are other solutions that work on multi-threaded applications. So you get into another area where if you're having multi-threaded applications, how do you know who incremented the counter last to make sure this whole system is safe? The whole system relies on single thread having an accurate count. When you have multiple threads and they're all contending for that one counter, that one piece of memory where the count is, the question is, how do you know that you're looking at the right copy? How do you know no one else changed it before you, right? So you have other things you got to get around with that. And it's actually not that complex. There's RC, which is reference counted, and then there's ARC, atomically reference counted. And then that works differently, and it solves that problem.
When I use ARC all the time.
Because there is an overhead for using ARC over RC.
Is it some sort of queue?
What's up?
Is it some sort of queue? The atomic one would implement some sort of queue.
Does it start with Q?
If it implements some sort of queue to.
It doesn't. It actually uses what they call, it's called an intrinsic. That's a name for a specific instruction that an Intel CPU supports. So not all CPUs support intrinsics, right? And that's what it's actually using under the hood. Your CPU has a notion of incrementing, which happens in one clock cycle, and it has the notion of atomic incrementing, which locks other things from manipulating that piece of memory for that one clock cycle. Okay. Yeah.
That means that if two of them are trying to manipulate it, then it will be, one of them is going to do it, and then the other one, since it's locked, the other one will wait until the next cycle or something.
Yeah.
Something like that, yeah. Yeah. You want to read the implementations on the CPU. It's actually from Intel will write the documentation on that. You can.
You get any runtime error if you have 2 threads running the
It won't allow it. When it tries to go to another thread, it'll say this isn't send. Okay, so now we're creating a reference cycle. Okay, reference cycles can leak memory. This is a good point. Rust memory safety guarantees make it difficult but not impossible to actually create memory leaks that are never cleaned up. Preventing memory leaks entirely is not one of Rust's guarantees. That's an important point, right? So Rust does allow it in some cases. It protects you against unsafe memory access and double freeze and that kind of thing. And writing to memory that's been freed right after free, it does not protect you from leaked memory. In fact, Rust allows you to leak any box. You can literally call leak with new, leak new, and put inside of it box new, and leak any pointer to the heap. And you will sometimes do that when you're communicating with other languages. You want to tell Rust, you are no longer managing this piece of memory, I've given it to C. You will leak that pointer, and then Rust will be hands off for it from ever. Pretend like it never existed. And now that pointer is leaked, and C can do whatever it wants with it. You drop the pointer. So if you're writing a memory allocator, you're allocating memory, you're putting stuff into it, you want to give it to another program, that's how you do it. You tell Rust, leak the memory. So now,
Or if you want to pass a string from Rust to SQL.
yeah. So now we have creating a reference cycle. Now we have a list of I32, and it has a prepend, right? So it's prepending an I32 to another list, and that list is a ref cell RC. So the advantage here now is that we can have a loop, and we can have multiple things pointing to different parts of that loop, or that loop pointing to multiple different nodes outside of it. Both of those things would work. And then we implement on that tail. And tail is going to take the self, and it's going to print everything until the end. It's going to assume that there is no loop. So this tail isn't smart enough to know whether or not it has looped around. But it effectively matches against self, and it's going to return all of the other items. This tail doesn't actually print it out. This tail is just returning all of the items except the first one. Does everyone know what tail means? Has anyone heard of tail? OK, if you've never heard of tail, I will show you my explanation of it. Let me see here, Evan Carroll. This is called the list monster. Head, tail.
Totally coming out.
No, there is.
Or linked list.
Where am I? There we go. This is how I like to explain tail. This came out a long time ago. That was the book, Learn You a Haskell. Learn You a Haskell presented tail like this. And this is the best way for presenting tail, in my opinion. There are different, when you have a list, you have a bunch of different elements, right? And the dynamic in which you're analyzing those elements is always this, right? They have different names for it, but this is usually the general premise here. Head is the first element on the list, always, right? Tail is everything that's not the head. In it is everything that's not the last element, and last is only the last element. Why do we always analyze lists like this? Because we're either operating on one element from the front or one element from the back. And if we're operating from the front to the back, we say I'm processing the head, and then I'm calling myself again with the tail. That's how that works. You're processing the head, and then you call that same function again with the tail, you recurse. And every time when you're processing it, you take off one element, you look at it, you call yourself again with the tail, right? You want to work yourself from the back to the front, you can do that too. Generally, it's slower, but not always. Some different lists work differently. And then you're going to look at the last element and call yourself again with everything that you left. And then when you call yourself again, you're going to pull off the last element and leave the rest of it and call yourself again with that. That's called recursion. You're calling the same function again, and you usually process one element at a time with recursion, and you usually give back to that function the rest of the work to be processed.
I'm guessing the last element is more prevalent in double-sided lists.
Yes,
Double-sided lists.
exactly. That's correct. I mean, you can use it in both, but it's definitely more efficient in a double-sided list and a doubly linked list. OK, so here's what we're saying here with tail is it's going to return to you everything that's not the head. So tail in our case ignores head, right, entirely. It's dropping it. That's what the underscore means. And it's returning to you the rest of the list, which is the sum item. That's a really shitty name for it. That should actually say, because cons is the first element and then the list. I would just say that. I would say cons underscore comma list and then return some list. XS is actually very normal. That's what people will typically write in there. But yes. So here's us processing this, and how are we on time? We got 15 minutes. So
Functional group always goes over.
what's up?
The functional group always goes over.
The function stuff?
The functional group. Yeah.
Oh, does it? Well, they should be here for this one then. This is all functional programming, right? The idea of like processing lists and recursion. If you like this kind of stuff, it's functional by nature. And we would say it's functional because you have no state outside, right? So you're providing all of that state to yourself. It's a very common thing in a functional language too. So we're saying let A equals RC new, and we're giving it all the rest of that stuff. So we have this reference counted list there, and we're printing the initial count. The initial count is going to be 1, a next item, and then we're calling a.tail on that. What is a.tail going to return? In the top, it is going to ignore the 5. That's going to get assigned to the underscore. It's going to return this. That is going to be the result of that a.tail. Right? Down here, we're saying a.rc count after B creation. Now we're getting the strong count, and then we're getting the strong count of B now. Why are we doing this? Well, notice B now has an RC.clone of A. And A hasn't gone out of scope yet. That means A will, the strong count of A will be 2. 1 for A and 1 for B. Right? And then the RC strong count of B will be 1. And then the B.tail will be this. It'll be the ref cell of the new, of the clone, of the A, right? And then we have here, if let some link equals a.tail. So if tail isn't the empty list, if it has stuff in it, then I'm going to replace the tail with the RC clone of borrow B. So we have A, and it equals to this shit. And I'm effectively saying the second part of it, this, I'm going to be replacing it with RC clone B. So now we're going to have A equals cons 5 and then B. This thing here. Okay. So now we're creating a loop, and we're creating that loop on A. And let's just go ahead and see where it prints here. So we got A initial RC count right. The a.next item is right there, ref cell, and then a.next item. Yes, okay, that's this at this point. That makes sense. I didn't realize that it was nil at the top. Nil, okay, and then we have this one, a.rc count after B creation 2. We went there. Why is it 2? Because now the B has a link to A, and A has a link to itself. The B initial RC count is 1. And then we're at this line, B.next item. B.next item equals B.tail. And B.tail is going to be this. So we're expecting it to say ref cell of 5 tail, nil. And then there we go, cons 5, ref cell, value nil. Now, B.rc after changing A to A.rc after changing A to. The only point that they're showing you here is that when they change this link on A, now we have both of them set to 2. Because A has a copy of itself and a copy of B, and B has a copy of itself, and we are adding a copy of itself to A. So now both of them show 2. And this is what we've created, this confusing ass thing. This is the reason why that they're showing you now you have infinite flexibility. You can do whatever you want. But Rust is not guaranteeing you that this memory will ever be free. Why? Because if you create a loop, this loop guarantees one thing will always be pointing to the next. It will not free it. There was a solution to that. Now we're going to probably go through the solution. Okay. The solution is this weak stuff. When you call RC downgrade, you get a smart pointer of type weak T. Instead of increasing the strong count in the RC instance by 1, calling RC downgrade increases the weak count by 1. RCT uses weak count to keep track of how many weak references exist, similar to strong count. The difference is the weak count doesn't need to be 0 for the instance to be cleaned up. So there is a notion of a reference counted thing. The weak count can get to 100. The strong count can get to 0. The weak count will not keep it alive. It'll go away, right? And the detriment of that, okay, so now let's think about this, right? Remember I just said that RC is unsafe under the hood, and it's only safe because of the interface? Well, now I have the ability to create this weak thing, right? And I don't know whether or not the type will live long enough to be used. Because a weak reference happens every time. It can happen when it's used, right? But it's not the strong type that's going to keep it alive. So if you have one type of RC and it's that strong reference, then if the strong reference is greater than 0, that thing still exists. But if I create two separate notions, a strong reference type and a weak reference type, and I'm saying as long as the strong type is greater than 0, the type exists, but the weak type can be anything, right? Now the strong type gets to 0, it may not exist, and the weak count may still be 100. What happens? How do I keep that safe? You control the way you use weak references. You can no longer make the assumption that because you have a strong reference, it is still good, right? Rust will drop even that assumption. And now what happens? Well, now when you try to borrow the reference from the weak type, Rust checks it then and it says the type no longer exists. Now you have a different runtime error. Before we knew for certain when we had a reference and we were a strong reference and we were using RC, we knew by the fact that we had that reference the type existed. Because Rust can only drop that data when the RC strong reference is 0, gets to 0. Now we created another notion, and now if RC gets to 0, the type goes away. Rust is free to give it up. But if there's still weak references, right, that weak reference, when you try to use it, needs to be checked to make sure that thing is still alive. So that's how Rust does it. Rust says, you have made it more difficult for me to ensure that this code is valid. I can't merely ensure it's valid because I haven't yet cleaned it up, right? Therefore, you now need to check that additional thing yourself. And in order to do that safely, you have to have a safe behavior defined for when you try to dereference a weak reference. And that's what Rust is showing you here. It's showing you that the weak reference, which returns an option of RCT. Now, if the weak instance is none, that thing no longer exists. And there's a way for Rust to represent it doesn't exist anymore. And that's what it's doing. Does that make sense? Anyone have any questions about the strong or weak references? Can you see where this is going? Why we're doing this?
Weak count, why do you need to keep the count of the weak?
Why do you need to keep account of the weak? That is actually a really good question too. I don't know.
So it's never used in practice?
I think the weak count is only used for 0 or not 0. I guess here's the answer. You should have a count of the weak because you'll never know when it's not 0 unless you're decrementing it. And when a weak counter goes away, you can still decrement it, right? So even though when you get to 0, nothing happens until you get to 0, then you know that it's totally gone, right? When you have the weak reference, if it's 10 and one of them goes out of scope, how do you now decrement the weak reference? You can't. If it's either 0 or 1, you can't. So the number exists there for the same reason, so you know when you get to 0. But nothing happens once you get to 0. The type doesn't get freed. It gets freed on the strong references getting to 0.
My guess would be if you have like before the
So why are
cycle.
you even decrementing? If you don't even care, if nothing happens. So once it's 3-0, you stop decrementing. But you don't even.
You do care.
Well, so if you have like the example before where you have a cycle, maybe you keep the counter for the weak reference and then you drop everything and then you check that weak is actually 0, otherwise there's a reference to that's basically a memory leak, right? So that could be a way to check after you dereference all this cycle if it's actually dropped everything. I mean, dereference everything.
I don't have like a real good canonical example of why you keep a weak count. It's according to this, which doesn't sound very good. A weak pointer is useful for keeping a temporary reference to the allocation managed by RC without preventing its inner value from being dropped. We get that. It is also useful to prevent circular references between RC pointers, since mutually owning references would never allow either RC to be dropped. We get that. But what's the point of having the count?
Don't know it's about 9, right?
Oh, okay.
We can stay later. It's fine.
Well, my guess is that.
There you go, weak upgrade. There's your reason.
Okay, so my idea is that you need to drop this value, but then you're dropping it before you remove all the references. So you need a way to know how to remove all the other references after you drop it, so that you don't leave references.
Let's see here. Prevent the allocation itself, the backing store from being deallocated. This is the key here. This is the answer to your question. Note, however, a weak reference does prevent the allocation itself, the backing store, from being deallocated. There's a distinction here between ownership and deallocation. This is another really good question. I have a feeling like this is a deep rabbit hole, and I'm also ill-equipped to answer that. The question is effectively, and by the way, this is it, we're done. You guys have stumped me many times today. So there's some things that I want to look into. The affect ownership, then why do we even need a weak count? Why isn't just the strong count useful? That's not to say there is no idea of a weak reference. A weak reference could just be an uncounted reference. Why isn't that satisfactory? And the answer is because there's a distinction between ownership and deallocation, and I don't understand that distinction yet.